Hello everybody, welcome to another stream. So last stream we designed the BVH node data structure, and we got started on thinking about how we was going to construct the BVH, and then we realized it was a little bit more involved, so I just sort of tried to understand the paper as much as possible. So off stream I did a little bit more reading into the paper. So yeah, here's the BVH node we designed. We packed a bunch of data and fixed it and fitted it into 16 bytes per node, so we can have 4 children and they should all fit in a cache line. This is the aim. And we so offstream I read this paper, which is linked to in this blog post. I'll link both now. There's the paper, here's this blog post. So I read the paper and I understood it a lot more. But yeah, basically when you this diagram here, I want to produce a version of this diagram with different data. So it will look slightly different. And write that on CPU side, but we can easily move the code over to GPU side because it'd just be a tiny change. So that's what I want to focus on doing today. So one key thing to notice is that this paper and this blog post operates on a binary tree of nodes. We want a quadary, I think that's how you say it. So 4 nodes. Yeah, up to 4 nodes up to 4 sibling nodes. So what we're going to do is debug, draw a diagram, and then make it all link up. So the basic idea, so I can do a quick little rundown. The basic idea is that you have your leaf nodes. These are like, say, the primitives or triangles, or, in our case, ellipsoids that you're trying to render. And you sort them by the Morton code. So the Morton code is a spatial curve. So it takes a 3D coordinate and makes it a 1D coordinate. So stuff that's close to each other in 3 dimensions is close to each other in a 1D array. So it does that with a Z curve. You might be thinking Z curve like this. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So basically you could have multiple triangles in the same bin, basically, but that's okay. So they're sorted in this order, and then they go over here and do another big Z, and then down here doing a bunch of Zs. So there's a macro Z as well as a micro Z. So that's the sort of ordering that they will be in. So the basic idea is that you can do this in parallel. So you can pick any single node. A thread can pick a single node, and just from knowing the node index, it can figure out, it can scan over these Morton Z curve. Yeah, I don't think I can explain it particularly too well. The basic idea is it can, if you're trying to process this node here and find its children, based on its node index, you can know where to start looking, basically, and then scan along and find where there's a difference in the bits, basically, and figure out where you need to start looking. So it's kind of they can run independently, so it can be highly parallel when it constructs the tree. So what I would like to do is just get debug drawing them out, make it so I can drag a slider and change the number of children, so we can see it work from a small tree to a slightly larger tree, and if we should get it to work across all those different nodes, and then move it to GPU afterwards. So what I'd like to do is open up my not screenshots. Right. So there is so we just need to do some UI, and I would like, where's the yeah, so we want to disable the PBR UI, and we'll do a new one. So this new one is the this tree. So we need to have a slider at the top where we can just cut yeah, I probably just want to do a cut top and then some form of slider, something like this. So just have a nice little slider called something like number of leaves. Or leaves count, whatever I want to say, right? Then so this be the number of ellipsoids that we're trying to render in a sense. So we can start this off at something like maybe we just want to do 4 to begin with. Well, not 4. Probably more than 4. Maybe we can do, yeah, maybe do 16, so there's 2 layers. Yeah, so then we want to draw the tree. So the way that I'm thinking about it is, at most we probably want to support up to probably about 70 odd of them. So that will get you like 2 layers and a bit, and then it can still fit on the screen, I think, as well. Because I forgot what that temporary resolution is. Right, 1600. So if we're trying to draw 72 nodes across, I've got to be careful here. Let's do 64 for a sec. That's 25 pixels each. Yeah, maybe. Let's just try it out, right? So let's just do a nice little for loop. We'll just go over the number of nodes, and let's just draw a bunch of boxes. So I want to like a cut top. Yeah, so this would be, you want to cut from the bottom and then just cut. And then probably just cut left a whole bunch. And then just do a bunch of text. Maybe. You don't need too many characters, right? 8 is probably fine. Your SN printf. Buff. Into there. And you'll just put a little piece of text in there. So you need at least 1 node. Right, so let's see what that looks like. Oh. Right, I tried to write a little bit more code to figure out over the weekend to understand this paper a bit more. But anyway, let's just get that compiling. Alright, so it compiles now. So if we run this. Alright, so clearly that's not what we expect. We want it to cut to the... Yeah, I can increase this. It's obviously the wrong way around. I'm using the wrong box, isn't it? cut rec bottom. Why is it doing that? Just do that once. Cut left. You probably got about, let's do 15 pixels. Right, clearly not enough for a couple of digits. So you need to up that. I think it's a 26 pixels is all that we had, I think. Let's try that out. Alright, maybe that's fine. Right, yeah. So it only go up to 64. Now 64 is the level I wanted to go up to because you get 4 layers. You get the root layer, which is 4 nodes. Then another, so you get 3 layers, I think. Oh yeah. 4 nodes, there 4 children makes 16, then 64. Maybe this is good enough. I've just got to maybe reduce the text size a bit. Maybe that's what I need to do. I can make a new style. Well, I could drop the... Well, I need the boxes because otherwise I'm not going to be able to see the text too well. But yeah, that's not really ideal, is it? So if I get the style, the UI style, we can do a custom one, and that will just make it such that we can just do whatever we want. So we can reduce the margin and padding down to that 1 pixel. We can remove the silly radius stuff. Border width can be a pixel as well. Where's the radius? Oh yeah. So radius we can drop down to 0. Right, just doesn't matter. And then the text size, we go down to 18 on that, give it a little bit more. So when we do our elements now, we can just call it box style. And that'll give us well, this one doesn't need it. Yeah, so we should have a lot more. Hey, Degra Dilla. Hey, what books do you recommend for writing a C compiler? I don't really recommend books. I don't really like books. I think they're too long. Yeah, I don't know honestly what to recommend for writing compilers. There is the crafting interpreters. It goes a little bit too far because an interpreter is obviously a compiler plus an interpreter, but it does a good job of at least getting into doing stuff practically, because I think the biggest thing is you just need to get some practical. So it's a free book. You can order it. But yeah, there's actually you can actually just view it online for free. Yeah, I'll drop that link. Put a better one. But you can also buy a copy if you like it and want to support the person. But yeah, they teach you how to, what is, basically was it an abstract syntax tree, and how to interpret it as well, which is kind of useful, and then also making bytecode, which helps you sort of understand like how to generate something from a syntax tree, and it'd be a nice your own cleaner bytecode, which isn't which is not some other more complicated bytecode, which you have to support or whatever. Because maybe you do LLVM IR, which is more complicated, or you'll emit direct x86 instructions, which again is more complicated. So this helps you sort of get that understanding, and once you have this understanding, you can move on and you'll know the terms to Google, and you can just basically go from there. Because there's a lot of resources out online, and I think you'll be better off doing that rather than picking up a book. And then also right, so that for some reason, because I still cut 26 on it, so let's cut 20 instead. No worries. Right. Let me bring that. Right, I think we're doing good. I can up that probably to 22 now, because that gives me more layers now, I think. My issue is though, there you go, 72 leaf nodes. So the thing that this paper does is it separates the idea of a leaf node and an internal node. So an internal node obviously doesn't hold the thing you want to render. The leaf nodes hold the thing you want to render. So what we need to do now is draw the internal nodes. So we'll just put those on the screen as well. So obviously these need to be positioned in a better place. But maybe they don't have to be. We'll figure it out. So we've got our leaf nodes in there, and we can scale it up and down. So the thing that we need to identify is the way the internal nodes are numbered is 0 is the root node. We don't have a root node. We're going to make it such that we have root nodes, and basically these will be our root nodes, and we'll have 4 of them instead of 2. So so the way the numbering works is 0 is the root node, then it goes 1, 2, 3 is the parent, and then 4 is the sibling. And then if these guys were not basically the root children, then it will go up more, but they are the root children, so it ends up going down 5, 6 is the sibling. Or 5, 6 is the child. Yeah, so what we have to do, I don't know how I'm going to draw this. So we'll probably go over every single internal node, figure out what the children are, and then draw it based on that, maybe. But then that means I have to get the algorithm right for it to render correctly. How do you know what depth you're at? Based on the range, you could know your depth, and then I could position it. But you don't also know what. Based on the range of the nodes, so this bar here, you can know the depth, maybe. We could also, just by the numbers, we could know. So 0, 1, 3. Yeah, Or maybe I could build the tree and then try and render it. And that would be... Yeah. So build the tree, then try and render it, and then if it doesn't render, then there's your problem. Yeah, maybe we'll do it that way instead. Hey there, Aposto, how's it going? Welcome. How are you? Yeah, so I might do a strut. We'll just call it node. Very creative man I am. So we can do everything with this. We can say we have a pointer to the children. So the node will want to know. So to render the node, we'll need to know the range. Its range, so I want to be able to draw that. Range start index, range end index. So I want to be able to render that. I then also want to be able to link to child node index. So because we can do any, yeah. So I think we'll have all of our nodes just sitting in here, static memory. We'll have at most, let's do 128. We don't have that many, but let's just say we have 128. Well, it's up at 256, who cares? So when every frame, we're gonna run this where we go over all of the internal nodes. Okay. We also need to have the Morton code, the leaf nodes. Leaf node, Morton codes. These guys, we should probably generate those as well with some seed. SRAND, isn't it where you set the rand? Let's SRAND, just some random number. So I can probably randomize the Morton code in a known manner. Wait, what's the number again? Yeah, we've got the leaf nodes count, isn't it? Leaves, or leafs, as I've called it. Broken English. And we're just going to store a bunch of random numbers in there and just say that's the Morton code. So we can just store index rand, done. Oh, it's here in it. Whoops. Cool. Right, so set up those guys. Neat. What's the next thing to do? Then, after we've generated those Morton codes, we can go over all of the internal nodes. Internal nodes count, which would be leaf nodes divided by 3. Because if you have a if you have a tree, if you have a binary tree with 8 leaf nodes, the number of internal nodes, which is the parent nodes only, that is number of nodes, take 1. But for 4 children per tree, per node, that's divided by 3 from my understanding. Also doing an engine, game an engine, my studio though. Awesome. Very cool, well done. But I coded a thing similar to what you did working on. That's cool. Oh, okay. Well, you done like a quad tree? Or are you done like some kind of like tree to help with the physics calculate? Or another type of tree to help with physics or something, right? And what sort of games are you making? An AABB tree. Hmm. Oh, okay. Yeah, it's kind of similar. So we're going to roll the internal nodes, and we want to then fill out this node thing, right? So this is where we're going to do all that. We're going to test out that implementation for that paper in here. So if we just say, so let's debug. I think what we could do is just marry up the ones which make. We're not going to do any magical thing. Let's just get the drawing working, I think. So let's just say, right, nodes, let's get the node, call it n. And then, maybe we, so what we could do, so it's a quad, so there's 4 children. Yeah, maybe let's say we don't have a root node. So we'll say, hey, see, the problem is the leaf nodes as well. Oh, shoot. Where are the leaf nodes going to go? I guess the leaf nodes will go after the internal nodes. How could I just quickly marry up these internal nodes to the... We could just say... Yeah, so what I'm going to do... So you got a number of leaf nodes, which means you need... divide by 4 needs to be the number of parents. So we could just marry them all up there. And then after that, it's another divide by 4's worth, I think. And I think you just do that. So I think we could probably start it off at... And you could start it off on... So you could start it off on the leaf node. So I'm thinking maybe we just do them sort of like perfectly in that sort of order. And yeah. So the children's start index would just be after internal nodes, and all the leaf nodes will start after all the internal nodes. Just in this example, so we can get it working, test the debug drawing out. So the child node start index is going to be, children's start index is going to be children's start index, and then we'll up this by 4 or something. Now, and then I guess like when the index when the index is equal to like well, I guess what you want to say like or we could just go down from the root of the tree. Instead, maybe that's easier. You do 4, 16. And you link up the internal nodes and then eventually you link up all the leaves. Yeah, maybe that'll work. That's probably the easiest way to do it for the debug. Just to test it out, innit? So we'll go over all of the nodes in total. So it's number of internal nodes plus number of leaf nodes. Wait, no, just go over the internal nodes. Yep. So I guess you would say you start off as 0. Yep. Start off at 4 to skip the first 4. So those are all link up there. Will that do it? So this one would get, so imagine this starts off at 2. I get these 2. This one, we get the next 2, those 2, nice. And then you move over to this one. This one will get the next 2, so that'll be these 2. Then this one will get those 2. This one will get those 2. Wait, did I skip one? Yeah, we get those 2. Let's get those 2. Right, so I think this is the same logic I've done for the 4. That should just build a quick little tree that we can use to debug draw. Yeah, so how could we, I guess we could start from, so how do we know how to position it on the screen? We could do a recursive function that just goes from the top of the tree. Or do you want to do recursive? You can maybe do a recursive function, or you could you see, when I implement this algorithm, the problem is I don't know if I'll be able to know the depth until doing another part, unless I do another pass over the tree afterwards. So yeah, I'm trying to avoid, like, I could easily put a depth in here in this loop that generates it, but I'm going to be replacing this with a different code that generates the tree with a proper one from the paper. So we just need a way to know the depth, I think. In 3D is BVH as far as I recall. Dynamic bounding volume hierarchies. Oh yeah. So I still think an ABB tree that you've done could probably just be referred to as a bounding volume hierarchy as well. All it means is it's just volumes which are surrounded by, yeah. It's just, you know the bounds of a bunch of children and you link out via a tree, right? So it could probably be a similar thing. But yeah, basically what we're doing is stuff like this. Nice. What's this used for anyway? Oh, box 2D. This is like 3D. Anyway, I'm confused. Oh, the guy who did it in Overwatch also did it. Sorry, the guy who did Box 2D also went to work in Overwatch and did a BVH. Fair play. Nice. I guess this one would have been done for physics then, on the CPU. So it's a slightly different problem, I think, maybe. Maybe not, though. Hmm. Yeah, what you did was a BVH. That's cool. I'll have a look at this off stream. Let's keep that around. Thank you. So what's the best way that we could discern where it could be drawn on the screen for debug purposes? Do we let's take these off. So we're going down these nodes and building. I could just take another pass over it. It'd probably be the quickest thing to do. So maybe we could go down the tree and get a depth. So I need to move this out, make a function. Node set depth. Nodes and so, and then you pass in depth as well. Just recursive function, easy. So 4 children all go next to each other, yep. You probably want a number of children. So, yes. So you probably just go over all the children and then recursively call the same function, but with like a +1. So it'd be nodes, nodes n children start plus index. Take the address, obviously, and then depth +1. Anything else? I need to set the depth, obviously, so n depth equal depth. Cool. So that'll do for now. So what we'll do is do something like a set depth, which will mean set depth on nodes, and 0. Cool. So this will then mean, so we need to set the children count. So we have to make sure that basically it's min between like +4 with the internal nodes plus leaf nodes count. Then you want to like take away the children's start index from that, and that'll get you the number. So that should be the demo tree set up. So let's just render it nicely, and then we can change this code to the proper code in the paper. No recursion on GPU. I'm implementing it on CPU because I don't want to crash and burn my GPU. If I do an out of bounds index and I want to debug draw it. I can debug draw on GPU, I've got it all set up, but yeah, I just don't want it to crash and burn. So I'm just, we're gonna implement the paper today, hopefully. But I'm just getting the, I'm just trying to debug draw something like this so I can make sure that my implementation scales from a small number of nodes to a large number of nodes. With a bunch of random data, basically. I use it for culling everything not visible and also for custom pathfinding algorithm. Nice. Cool. Ah. Yeah, trees are complicated. They always fry my brain. Right, they try and make a balancing tree as well. Hmm. Yeah, I guess balancing tree is... Well, they balance it. Oh boy. Because this type of tree is that the left and right nodes don't matter. So it's really easy to balance. Huh. Left and right nodes don't matter. But yeah, you reorder it and it will change the way the box is built, the bounding box is built, the shape. You shape... Yeah, it changes the... Yeah, the order doesn't... It does matter for performance because it will change the way you... It depends, like... Yeah. Like... Yeah, it changes the way the box is built. Or is that just in 3D? Hmm. Yeah, it changes the way the box is built, I think. So the shape will be different. But yeah. I think deep is fine sometimes if you know that it's an area that's not going to get... You're not going to go down much, right? The trade-off could be that you own that, you know, if the tree goes really deep in one place, but you rarely go down there, you've just saved a whole ton of time because you've decided to not, like, that's where the least common stuff goes. But yeah, it really depends, I think. Obviously, yeah, it sucks when you go down there, though. Right, so how can we now draw this tree? This silly little tree that we've made. How can we deep it? So we've got a depth. So if we have a depth, what does that mean? So I guess we'll have a max depth. So we'll just go, oh. So ideally they'll be stuck in here, so we just say max depth. And I think we just keep setting it. No, because you'll come back up and go down again, so you want to do max. And then we're going to make sure we obviously set this to 0 here, and voila. So, right. So now we know how many layers to do. Yeah. Right, so if we debug, draw this by going over all the nodes. So you don't know... See, with the depth, how do we know... So this thing makes the tree. How do we know what our root nodes are? Well, I guess we could guess that. But yeah, we need to start from our root nodes as well. So probably would be good to find... So your depth would be, oh no, you can't find out, can you? So we could probably say, parent index, put that in there as well. So we can start it, well, it'll be an index plus 1. So we know if it's, so we'll say, all right, well, we've picked up these 4 guys. Well, at most 4. So we'll go over all those slots. Nodes. And I think we'll say their parent index is equal to index plus 1. And then so that means now here, we could probably just do a quick scan and find where the root nodes are. We know they're at 0 right now, but when we implement the proper algorithm, I think they'll be somewhere in the middle. So we'll find those here. So we'll say root nodes start index. So we'll just do a nice for loop over all the internal nodes, and we'll just go, okay, if nodes index parent plus 1 is equal to 0, then we know we've hit one of those, and we can just break. And then we'll basically set this to index, right? Yeah, so that this should be in, yeah, and then that's the root node start index. Cool. So that'll go down the tree, and nice. So when it comes to drawing the tree, what's the best way to do that? So we could do recursively. We could say, so I know the maximum number of nodes I want to try and visualize here. I think it's like 72 or something. So we could just do the recursive descent again. Maybe I don't need that depth thing actually. Maybe what we do is we say, the depth will be passed in, but we can use that. So the root nodes will go in the middle at the top, and then the children. So I guess we go one node. Yeah, we can space them all off over the screen. There'll be a spacing that we could plug in, and that spacing will. So you go over all the nodes. We have some kind of that's the other tree. Yeah, so forget this root node. We want to have a root node. We'll have root nodes. So yeah, you probably have a larger spacing for these. Then the children will start off at a certain place. With half the See, my problem is yeah, we won't be able to link it like this though, but that's cool. We'll just draw arrows. you're able to work out what the children will be. So you work out what the child would be, and then yes, I think we'll just say nodes draw. Be recursive. We could probably say so we'll start this one off at the middle of the screen. Or we could just say, hey, it's got this area, and we'll use the center and put it in there. And then we'll split it into quarters, and then assign that box down. Yeah. So I think we'll say, yeah, we'll pass in the whole box. So where's that box? Rectangle, right? Yeah, so passing the address to rectangle. And you'll just keep cutting that from the top. That won't work, will it? Yeah, I think that'll work fine. Yeah, so let's take this. And we probably want to take that star with us that we made. Not that it was anything too complicated. Just so we can pack everything on the screen. So here's that function. So we just drop that in there. Right, so the basic idea is this is going here, I think. So the rectangle comes in as a pointer. As we cut from the top via some amount. And then we want to put our node in the middle of that box. So we'll do something like this. Don't know why the crap this is being like this. Yeah, so we put our node. So what is our node index here? We've got node pointer, isn't it? All right, we'll make it get node index 2. So that is n take nodes. Voila. And then we'll put that in there like that. And what we'll do is yeah, cool. So this will display our node in the middle of that area we've just cut. Now we're going to go over all of the children. Wait, what's that doing there? Yeah, we'll go over all the children. And those will get a box. Those will get a box. So we need to split it evenly into quarters, right? So you want to take that child width. You want to get the width of the that rec. Maybe we should pass it by valley. It's just demo code anyway. All right. So this would then be a UI rectangle dims. So when I get the width of that, so address of rectangle, divide that by 4. And then that is your child width. So you keep cutting to the left. What's going on with this? Yes, we keep cutting to the left. put that in A, I guess. So we keep cutting that rectangle to the left, cutting it up, and then producing these smaller rectangles, which then get passed in by value into the child. So that should... Oh, dot x, I meant. Right. We'll cast that to an int. Do nice to truncate. Right, so that should just put a number down on the screen, basically, in a box. So let's see how that looks, and then see where we'll go from there. Right, so clearly something is buggered up. So a 0, I can't see a 1. Oh yeah, we didn't go over all the children. Whoops. So because we have 4 root nodes, we actually need to do this for the initial call. So that, yeah, maybe I could have done it a different way, but it doesn't matter. So when we call this initially, we need to say, we'll go over all those root nodes, there's 4 of them. We'll say there's minimum of 4 nodes. Where's that? Yeah. Right, so we go over 4 nodes, get that root node. What are we doing? So from root to root plus 4. So we'll go over all those. We'll cut the rectangle to the left. Cut. By the child width, and then we'll simply pass in IDX. Alright, let's give that a go, see what happens. Alright, just a bunch of boxes, and I don't know what's going on. Oh yeah, we didn't put it in the middle. We didn't center them. So the cut should happen, cut left by that. Or I should have put A in there, and then we should have put them in the middle. So we need to put this cut's left by 22, whatever. What I would like to do is center it. Center horizontally A. Alright. So that should be what we're looking for. Right, that's looking alright. Just need some more vertical spacing. Yeah, need some more vertical spacing. I don't know why that's going down the... Oh no, that should go down there. Yeah. So I want... Yeah, so these obviously have these 4 children here. So we could probably color it. But yeah, we need to get them to link up. So we'll put more depth down on it. So when you cut the top, you could probably do another bit of a cut on it here as well. Let's see what that looks like. Yeah, so that's doing it. You know, we could do more. Let's do maybe 90. So we get some nice spacing, draw some nice arrows. Yeah, so now what we would like to do is link these guys up. So these where the children go here. See, I'm probably fine just to go up to 64 leaf nodes. I don't know why I'm not seeing a number. I didn't do the number up here. But yeah, let's limit to 64 leaf nodes because that's enough layers. 64 leaf nodes. So that should do a few layers, and that should be enough for me to figure out if I'll... Alright, 63 then. Yeah, there should be enough for me to figure out if the algorithm I've implemented is correct. So just got to link these up with some nice arrows. So we have an API for that. So we can draw yeah, my draw 2D goes on top. I can get some nice vectors. It goes on top of UI. So we know the screen coordinates. So you know where the children are. You can work out where that is by doing something like this. So you can work out where that child is. So we take a copy. The child box, let's call it. So it's just a centered version of that. So I could just draw from the parent to here. So the parent is somewhere like, so we need the center position of that. So, or bottom center. So I need to be able to say something like parent point, I don't know. So that's going to be something like, so on the X, that is UI rectangle center of the A rectangle along the X. And then you want the bottom. So that is just A dot min Y. Because we have bottom left origin. So that should, they want to be floats, but whatever. Oh, no, I think we want to do floats actually. Thinking about it now. Right, so got that point, and then we just need to get the point for this child box, but we'll do at the top. So it's just the max Y, and then we want to use a child box instead of, so this would be the child point. So now we just draw that lovely vector, so we just use draw through 2D, a vector, yeah, draw 2D vector, position, yeah, so drawing towards child point, wait, from parent point, and do subtraction. Wait, these are, what are these? Yeah, they're floats, good. And then we do a subtraction going towards child point from parent point. And then we can do like, I don't know, a few pixels, 4 pixels, maybe it's too much. Then, well, it's like a depth, isn't it? Okay. 4 pixels thickness, then color. Let's just do white. So just do color or white. And voila. So that should. Why does it want to? Oh, okay. Did a vector 3 instead of vector 2 sub. Right, so we run that. Cool. So got our errors now. That's nice. So as we increase it, you see. Cool. Yeah, so this is a tree that we've hard coded. This is obviously not going to be. What we need to do now actually is put the Morton codes down here, because one of the key things about this is they have Morton codes, and these we're going to want to debug these to help us understand where we're going wrong and all that. So I could probably get by with just doing them on the leaf nodes, so we'll do that too. So say if you're a leaf, so in the draw, we need to get your Morton code. So we'll have the Morton code here. So we can, so I did this like leaf. Oh my days. So yeah, leaf Morton codes. We'll get rid of that. For crying out loud, what did I do? Leaf Morton codes. We'll get rid of this, but we'll move it. Instead, we'll say, you know what, use nodes. Need to start on the leaves. Let's get this up here. So that would be leafs start at internal nodes after the internal nodes count, and we can then poke in their Morton code, just some random integer. All right, so now we've got the Morton code in there. When we do the node draw, we'll just vertically lay out all the bits. So it'll be nice and fun, get to do some bit stuff. So basically, where we've drawn the node, we'll make a new rectangle. No, we won't. Here, we'll say if, I don't know, if Morton code is not equal to 0. Where's the node? N. Right. So here we'll just pick away at the code. So we'll just do something like this. Code. And we'll just go down from most significant bit to least significant bit, I think. Oh, Embergs, thank you so much for the sub there. Really appreciate it. How you doing? Appreciate you, sir. Give you the Bulmer salute. Right. So I think we could just take that rectangle, move it down, change the. We probably should change the color and change the style. Yeah, we'll do another style quickly. Wait 2 seconds, I just gotta ask my wife something. Go back. All right, welcome back, folks. Yeah, so I wanted to have this like the Morton box. I don't know. Just the style for the Morton code that we're trying to debug draw. So we'll just change the box color maybe. So we're using like gray ones here. We can use brighter grays. And then maybe we could change. Maybe we could do gray 8. Oh yeah, gray 8. There we go. Maybe we make it, or maybe we invert it, right? Maybe we just go, hey, you've got a A and a 1, right? Yeah, so it's just inverted. So we'll use the Morton box instead. So all we're looking at doing is just like basically taking that box, which is A here, and just shuffling it down by like evenly, basically, I think. Just trying to do something like this, right? Maybe what we do is we could just do one big box and just do the bit string. Yeah, so maybe. No, we'll do one box at a time. So a.min.y plus equal, I don't know what it was, 20. There's a line height and a bit of padding. 18 line height, bit of padding each side, 20, probably 20. 20 pixels, and then the max as well. So you do that first. and then you'll draw it, and then you need to sn printf into that buffer the code. So I think you want to do the most significant bit, I think. So you go over all the bits. Just call it bit. And I think you want to do code shift right. Yeah, do most significant bit first. So you invert that. And then boom, we'll give that a go. So that should display us a nice more code at the bottom for the leaf nodes. Maybe not. Oh, that was crazy. So clearly I messed, oh yeah, the parent point got messed up now. So what we need to do is have another rectangle. We'll just chuck that in there, call it B, B, B. And then we'll be that one. All right. So let's see how that looks. Right, clearly something funky is still going on. What am I doing? Oh shoot, I'm not anding the little bit. So it might be going. I just want to and the first bit. I want to check one bit at a time. Right, so we should be seeing a bit string on these leaves, but we're not. So why? Well, we're definitely getting in here. There's probably something to do with a clipping rectangle. There's probably something to do with a clipping rectangle. Can I do something to... or I could just draw some text instead. If I draw text, does it use the clipping rectangle? Yeah, it will, it will. It will use it. UI clip rec. Yeah, maybe we just set the clip rectangle to the whole screen. Just hard code it. Let me go to the UI. Clip shape finish. And I have to set current. Clip and rectangle, and that's accumulated. Yeah, so I could just do one from scratch, and I have to make sure I set it. So for that, set current. Huh? Oh no, it would have set the current. Clip rec word start index. Am I gonna not be able to set this? Oh no, they will just restore it afterwards. Okay, that's cool. Yeah. So I just gotta put in the rectangle. We'll put 0 in the middle of the screen, and we'll say, you know, just do a just use that. I think we've got a temporary screen width and height because we haven't fully done the screen resize just yet. So the radius would just be 0. Center of the screen, well, it's this divided by 2. All right, I think that'll fix it. Demo code. Right, we're seeing stuff now. So what's to do with the clipping, but obviously the box is... It's a bit strange. Let's not draw it, and let's see what happens if we change that clipping shape and see if it causes the glitches still. Right, there's no glitches. Okay, so when I do this, it's clearly wrong. Oh, uninitialized memory, that should just be equal to A, and then we move it. Whoops. Right, that should be it. Okay, so they're sprinkling upwards. So I clearly incremented them rather than decrementing, and they're pushing along because it's mutating the box here. So I guess we do another copy, call it C, put that in there, and then we and then I want to negate it instead of increment because yeah, coordinate systems. Right. Yeah. Kind of going all right. Well, this would have been zeroed. Oh, the number of internal nodes change. Whoops. So we should go over all the internal nodes, set them to 0. I'll just do it. And I think there's a bit too much, we should make the Morton codes a bit smaller maybe. It still crashes, my life. But we're getting there, right? We're seeing the Morton codes here, a bit big though. Hey Davros, thank you. Appreciate it. Yeah, you know, because last time when I did the BVH, I did it on GPU, and then I settled for something more simple. But this one's like way more complicated. So yeah, just thought it'd be a good idea to, you know, fully visualize it properly and implement it on CPU and then just move the code over. So right now we're just doing we've got a basic implementation. So we've just hard coded the tree, or programmatically done a simple tree where the nodes are ordered in yeah, they're just ordered in this way, but soon we'll implement the actual algorithm properly. So that's cool. Yeah, definitely. It means that my implementation will not have bugs because I would have found them all. Because I'll be able to, I can randomize, I can change the Morton code, which changes how the tree gets connected. So I can change that a bunch of times and scale it from a small tree to a big tree. And it should, I should be able to roll, change the random number if you, like, I don't know, 12 times or something. Or maybe more, test them all out. And if I don't find any bugs, then we should be good. Maybe more than 12. But yeah. Should be alright. So yeah, what's the problem? So should we fix the try to figure out, does it crash because they get drawn off screen? Or push many? We have filled up the number of somethings. Words. So we're drawing way too many UI elements. Okay. Well, I know how to fix that one. Engine UI shared. Where's my 64? Chunk draw commands capacity. Alright, okay, whoops. Should be alright. So I think that one's inside the where are you? Ah, here we are. Alright. Ah. Right. So we double that number. Ding. Clip words is probably fine. Let's try that. How's it going, campaign? How you been? How have you been? Right. Ta-da! I don't know why that one loses its number though. It doesn't think that one's a leaf node anymore. We need to fix that. But yeah, we also need to fix the fact that these are obviously too big. But luckily we've got another. How have we got another? I think I changed that, didn't I? Morton code. Yeah, I didn't use the Morton box style, did I? So I think I want to change that line height to, let's say, let's do 12 or something like that, because yeah. And maybe we get rid of the border so it just is a bit small. Let's make them a right, they're stepping by quite a bit. You know what, let's do 16. We'll make it so they don't have a border. You know, probably no margin or padding. Who cares about that? We don't really need a border. And just waste space. So we could probably get away with just doing a 16 like that for each bit. Cool. Yeah, I was hoping to make the color actually just be where's the text color? Yeah, probably just make it black. And then I might just take it back to, you know, we'll do a light dark background. You know, maybe being different was fine. Okay, sweet. So the starting off color is starting off needs to move it down a bit, I think, by something. Nice, so now they're a bit separated. Cool. Maybe the white is a little bit too punishing to our eyeballs, so maybe we should just change that just a little bit to maybe like a gray 5 or something. And then gray 3. Oh shoot, sorry, lighter. Oh yeah, we'll do like a 9 then. Right. Go back to the grey. All right, so right, that's cool. So the next bug before we implement the actual algorithm is the fact that this node here should show its bit string, but it's not. The Morton code bit string. So the reason why that is probably just because the number of internal nodes. Could it be this? I don't know. Hello, I'm knowledgeable about multiplayer games. I know some little things, but I'm not an expert in it. I've tried a little bit of multiplayer programming. I did basically a lobby system, and I started doing the game bit, but I didn't, get much further than that. What do you mean though the colors unlike in Tailwind? I've just hard coded a few colors. So these gray ones, we've got black, gray 1, 2, 3, and that's just in 10, 10, 10, 20, 20, 20, and it just does it evenly across all the channels. And I've just got some other colors as well here. Each colors they have a shade. Ooh. Interesting. Yeah, maybe I should do something like that. That sounds sensible. Just do like a hue and brightness, isn't it? Or hue and value. Or hue and lightness. But yeah, maybe this sounds kind of sensible. Do it based on hue and give it a name. We'll have a lot of stuff, but it'll be cool. Yeah, what for the purple and that? Oh, funny. But yeah, it's not a bad idea. Maybe probably going up to these though, like the actual colors, and down. You probably don't need going past that, but yeah, it's cool. Not a bad idea. My face. Um, 2 seconds. Just got a message, my dad. Need to pick up a spare car key. Right, done that message now. Right, so what's the next thing? So yeah, the Morton code thing, like it did a thing. So for some reason 20 is not showing up. So like, what? Let me print out the number of internal nodes and figure out what the crap is going on. I want to know if 21 internal nodes, eh? Lies. As you can see here, that is not correct. I think that divide by 3 might be wrong. How many leaf nodes is this? Well, I should have printed out leaves as well. Someone made a generator. Oh, you could generate. Nice. I'd have to invert some of those, but that's cool. Like invert it the other way around, but nice. You export the whole grid. Money. It's pretty cool. But yeah, I'll have a think about that in the future though, for definite. When I do some more UI work maybe, like proper colors. For now, I'm just sticking to black and white. Right. So these are saying you have 63 leaves. Quick maths. That is 63. That is 64. Hang on a minute. Yeah, 63. Yeah. So. But it's really convenient. Sometimes you need a slightly lower, darker color. Exactly. Right. So I think it's looking all right. Oh. One more leaf node and then it adds two. What is going on? Oh yeah, because one of that goes there or whatever. I think. Huh, what is going on with this? You know what, let's go from the beginning. One internal node. Right, let's think this through for a minute. Oh, one internal node and four leaf nodes. Ooh. What is this going on with this numbering? Oh. This should have been zeroed from the beginning. Core zero array. I think so. Just rebuild it from scratch every frame. Right, four leaf nodes. You never want, yeah, I think the divide by 3 is wrong. Because, well, actually, this is talking about if you have a whole tree. It needs to be, I don't have a single root node anymore. I got rid of that. Meaning, the numbers divide by 3, take 1. Right. Divide by 3, take 1. I gotta remember that. Interesting. That's cool. We can work with that. Right, there we go. And there we go. Wait a minute, what is this? Where's my 83? 83 is missing. Right, one node. No. No. When I put it at 5, I didn't see anything. Oh shoot. The -1 was too late. It needs to happen first. Or to swap from blue to red while keeping general lightness. Yes. That's why hue, saturation, brightness is a good color thingy. No. Maybe it needs to be take 4. What have I done? Yeah, I think we gotta, because we haven't got a root node now. Right, let's put that back. So if we put it back to the beginning and we so my quick code, which is just meant to build a quick tree, obviously. Or is it because of that code? It's gonna... So your 6 leaves. Oh, it's always gonna take... And this should take a leaf. Should we deem this as a bug? Because it's just the algorithm that's built the tree that's the problem. It's still got the correct number of nodes. I think that's the better way of saying it. So my issue is though when is it a take 1 at the end we need, or a take 1? And then you need 4 internal nodes on the next level. Shoot. Those 4 internal nodes shouldn't be drawn. Yeah, I'm drawing the 4 internal nodes way too early. That's my issue. I shouldn't be drawing those. So you need to know... so I think I do need the root node back. Because, well, so the reason why I didn't want the root node is because on the GPU I don't want to waste. My root node technically exists, but it's going to exist outside of the BVH itself. It's going to exist in the instance data. Yeah. Yeah, it's going to exist per instance rather than in the BVH. Because you would have already tested against that object, and then you'll go inside the BVH itself. So So I think for these purposes, we'll bring it back. So yeah, let's bring it back. So we just do that. We find the root node, start index. Let's rename it so we don't get confused. And then we'll just plop that in there like that. That'll go over all of them. You want it to have the whole space. So it should just be rec passed in. And I think that should be it. Just so the math ends up being right, you know? Right, so 0. 4 leaves. What? Yeah, so you're going to waste. Huh? Right, so the root node. You start from index 1 for the children. There we go. Alright. I think that's right. 63 leaves. I think it's a bit off. Internal node's 21. So there's 21 internal nodes where it goes up to 20 from 0. And then you go from 21. I think it's missing a final node. I don't quite know though. Yeah, something's still off. So up it from 4 to 5, doesn't change. Go to 6, it changes. Something clearly wrong there. Where is that? So is that in? It's probably this here, this capacity. I've just messed up royally here, isn't it? So I think maybe. So when we have 5 internal, when we have 5 leaf nodes, we got 4 leaf nodes here plus internal nodes. That's 6. So you're saying 1. I think this is 1 going to be linking to. Yeah, 1 should be linking to. Yeah, so 1 plus 4, so you're on 5. So you're going from 5, 5, 6, 7, 8. But you've only got from index 5. And 6. What's wrong? One internal node, 5 leaves. Right, so this is only going over all the internal nodes, isn't it? Right. So it's only doing that once. So it never reaches, it never counts the other one as an internal. This is an internal node, right? Okay. Okay. So I think that divide by 3 might be a bit off. It might need to be the divide round up, maybe. Oh, raid. The idea of Alan, how's it going? Thank you so much for the raid, sir. How you guys been? Welcome, raiders. How did the stream go? So we're currently working on adding support for a bounding volume hierarchy, implementing these 2 papers, or this blog here, which then reference this paper here, to do in parallel on the GPU. But I want to, because it's on the GPU and programming for the GPU is absolutely terrible. Although I have got some things to help out. I've got printing and I've got debug drawing. But if it crashes, it crashes, it brings down my desktop, and if I and I also don't get recursion as well, which is kind of helpful for debugging, especially for trees. So right now we're just working on a way to debug draw a tree, how it will look structurally, and figure out if our tree has been constructed correctly based on a certain number of leaf nodes. We've also, got these modern code things here so we can analyze what is correct and what is incorrect. Yes, that's what we're working on. We're nearly finished with this debug drawing, just fixing a bug or 2. Make some progress on the stack side better. Cool. Awesome. You building that to show off your projects that you're doing. Thank you. Yes, the number of leaf nodes is maybe wrong. So I'm thinking you've got, so when you have 5, you divide that by 3, you get 1.6. So really should that round up to 2? If you've got 4 divided by 3, you only want one of those. So I don't think it's divided by 3 then. 6 internal nodes. So you need 2 internal nodes. When you reach 4, wait. 3. Crap. It might be a bit funny. You might have to say, take 1, divide by 3. That might be the logic. See the number of internal nodes for 4 children. Alright, 0, 1, 2, 3, 4. No, clearly not. Wait. And then it'd be a divided round up. Yeah, it'd be a divided round up. So you do a core divide round up. Maths. Right, so you have 4 to 5. There's 5 leaf nodes, right? Nice. 6 leaf nodes, 7 leaf nodes, 8 leaf nodes. Ugh. Right, seems to be working. Seems. Did I? Yeah, it's working. I just limited it to 63 because I had a bug and I changed it thinking that was a problem, but yeah, 64. Sweet. 64 leaf nodes, and that'll fill out the tree. Oof. That's what we want. So, yeah, now we've got this in place. We can start implementing the actual paper now. So there's two parts to it. Yeah, there's two parts to it. These are a bit thick though. Should we remove that thickness for that? Those two. Just a little bit too thick because I think we might. That didn't change a thing. Right. Good. Cool. I think the one we cut is a little bit too far, so I can't see the full Morton code, which is a problemo. Yeah, neat. So, nice. So, right. Okay, so with this paper, the basic idea is each one of these leaf nodes represents something you want to draw in, you know, it represents that primitive you want to draw. In our case, it's an ellipsoid. And you know, the way I've decided to do it is, yeah. So each one of these is an ellipsoid that we want to ray trace against. So we need to be able to construct the tree such that the parents point to the children. So the way this algorithm works is you can do it in a highly parallel manner where each thread can just literally get one of these internal nodes, as it's called. So you can just pick up an internal node, and just with the index, it can work out what the children are. It doesn't know it right away. You have to work it out a bit. So, and the reason why you have to work it out is because there's a preferred, it kind of constructs it to a nice, what's the way of saying it? To a reasonable quality for ray tracing and build time. So it makes a good trade-off between, so while you construct it, it takes a little bit more time, but it constructs a nicer tree to ray trace against. I think this is, there's another one called the linear BVH. Yeah, so this one improves on that linear BVH. Wait, is this the right paper? Sort more code generate subtree. Sorting effectively groups primitives close to each other. Yeah, so I think we're implementing that sort of linear BVH one. So it does it in a, so the speed, so I think this is, did I link the wrong paper? No, but this one's the improvement you can make afterwards. Is it? Wait, I'm getting confused with my papers. Oh yeah, this is the one where you can optimize it after. We're not doing this one. Yeah. So, where was I going? Let's get that one out of the way. Yeah, so the basic idea is you sort all your primitives via the Morton code Z index. So if they're in 3D space near each other, they'll be close to each other in a 1D array. So you sort your primitives via that. And then with the internal nodes, you can basically start. They've got this thing where they can determine. You have your internal node index, and there's this determine range function. There's an implementation online somewhere like here. And the basic idea is you have to search. What is it? You'll start searching here or something. Say you've got 1. You start searching here in the leaf nodes, and you'll do a scan. You'll compare 2 at a time or something, and you'll say, do a count leading zeros on the bits, and you'll see when do they start differing, basically. So you can know where the edge is. So they differ here or something. So yeah, I'm not quite sure on the exacts, but yeah, the basic idea is wait, where's the here it is. No, there's a better diagram. Here's the diagram. This is what I'm talking about. So if you construct it from the top to bottom, which we won't be doing, you can see that this bit differs. So you can imagine like each bit representing going left or right. Right, left 0, right 1. But it can skip if they're both the same. So yeah, right 1, left. But then this one here, yeah, it's not quite exact. It's not exactly that. But it's the basic idea. Right, so let's try and implement that paper, the algorithm now. So there's this sort of like pseudocode here for this, which determines the range. So given a internal node, where is the range of children? So if you have 3, for instance, the range of children is 0 to 3, right? And there's a way to work that out using this. Furthermore, if your node is 1, internal node is 1, your children are from 0 to 1. So you need to first determine this range of nodes. And this is what we're going to look into implementing. But the problem is this works for a binary tree, I think. Whereas I want to work it for I think it's called a quadary tree. I don't know, 4 children at most. So we're going to implement it for a binary tree, and then we're going to see how it actually looks. Yeah, see what we need to change. So there's an implementation here. We're going to implement it using right, so this is going to be the debug version, which allows us to see the tree. But we're going to do another version where we actually go over all the internal nodes, and we're going to do the algorithm. So there'll be this determine range. So we're going to get some form of range that we've got to calculate. And I guess we can just stick in a while loop so we can break out. Yeah, just so we can break out easy, and so I don't have to do a function. Wait, is there actually a loop? Yeah, I think there's a loop. Whoops, wrong one. Sorry, 2 seconds, just got a text. Hey there, Alex. How's it going? How you been? How have you been? Yeah, so I think we just return at the end of the function, so that's cool. Right, so they implement this thing called determine range. Where is it? So we'll just do a similar version to this. Let's see how it goes. So if we're on the root node, we'll just break set range to 0 to num leaves. Num leaves take 1. Yes, this gives you a range over the leaf nodes. So our leaf nodes are stored after the internal nodes in memory. So leaf nodes. Yeah, so we'll copy this code and then have a think about how we're going to do it, because the number of leaf nodes, like we have less internal nodes. A binary tree has number of leaf nodes take 1. We have number of leaf nodes take 1, divide round up by 3. So this is going to give us less nodes. So I think we need to sort of do the inverse when we're saying, when we have a leaf node index and want to calculate, when we have an internal node index and want to calculate a leaf node to start looking from, we have to kind of do the inverse of this. So do it the other way around. Range. So yeah, this is when it starts looking. So this will be your node, your internal node index comes in. This will look in the Morton codes. So I should probably put those Morton codes in a actual array somewhere, like I had before. Leaf nodes Morton codes. So I should probably actually store them in there. So index take internal nodes and put in, copy the same value in there. Okay, so now we can just fish them out easily, or a lot nicely. So we want to be able to know that leaf node that we're going to look at. So if I'm going from the internal node index, I think, so it's done divide round up. So I think you multiply it, then add 1. Maybe. Or maybe you just multiply it by 3. We'll just try that for now. So you grab, so that's the leaf node you're going to look at, and you're going to pull out some kind of, I guess we can call it self code, like they call it here. Now there's this function called common upper bits. They use these to figure out, given 2 Morton codes, how many of the bits are the same. So it's basically an XOR and a count leading zeros. Yeah, so something like this. So we need to really, what I really need to do is figure out how can we do that easily. There is a built-in, and I don't have to make that cross-platform. So I could probably just do common upper bits, A, B. I think it's built in CLZ X or B. So for each bit, right, if they are this, if they're the same, they'll be 0, and if they're not the same, they'll be 1. So it's basically a not equals across all the bits, and that would give you, when you do a count leading zeros, so it counts from the most significant bits, right? And it returns you how many bits are 0, so are the same. Pretty clever. So from there, we can do, where's the bugger? Oh. Right, here we are. So we want to get that L dit, what do they call it, L delta? Between self code and this plus 1, minus 1 plus 1. See, this is where it might be okay, or we might have to change the common upper bits thing, because it's working with a binary number. I think it might be fine for a binary tree, but I don't know still. R, then got this delta thing, this difference rather. So if the R delta is greater than L delta, 1 minus 1. So this says what direction do we start searching in? So there's a, wrong paper. I'll close the other one. So there's a, say if we, for 1, we start searching in 1. It takes the delta between this one, so this would be 3. You got 3 common bits. This one you got 2 common bits. So because you've got your right, is the right bigger than the left? No, it's not, so minus 1. So we search to the left. So we'll go and search to the left-hand side instead. So this node here should have this child, these 2 children. So that's the basic, that's a very simple breakdown of that. So right, so that's just a min. Alright. Delta min. L delta, R delta. Right, so it ends up doing these. Yes, so I forgot. Yeah, this is added in by this person who's made this code here. So in the paper, it doesn't really mention this. So it's saying compute the upper bound for the length of the range. So it's starting off. So let's just ignore this for the moment. so maybe let's just read this. So that's the first bit we just did. The second part is storing this sort of like this min. Right, maybe it's calculating it there. Maybe this is what it's trying to do. Delta. Right, while it's greater than this, S min do this. Right. Right, so the S min is there, delta, cool. So okay, so this person just optimized this away by doing like a min between the two that is cached. Right, okay. So that's fine. This those right, so delta, so it's starting off delta's -1. Right. So this function here is basically doing that common bits thing. That's what this means. So our common bits, I plus L max, multiply with D, I guess. Greater than it at the min. Do this. Yeah, I don't know why. Is delta used elsewhere after this? Yeah, it is, right? So, right, so if I temp, so it's got a bit of a safeguard on it as well. So internal node index plus this D here, which is either -1 or 1. Right, so it's a signed number. So if you go out of bounds, just, yeah, sorry, if you're in bounds, then bother doing anything, right? And then it's set -1. Okay. So you could go out of bounds. So that's all that's doing there. Right, okay, so right, seems pretty legit. Yeah, and then it's doing it again. This other check again. Index. Let's see. So otherwise, you're going to be equal to -1, right? And therefore, you're not going to do any of this. So then you're find the other end, but in the binary search. So what is this one doing? Compute the upper bound. Yeah. So this code is about finding the most right node. This code is about finding the most left node. So right, it just does a bunch of balance checks again. So yeah. Right, so I think let's just bring this in and just adjust it, and then we'll adjust it for 4 nodes, because it's basically what we need. Let's see if we can. See, once we get it working, I think I want to try and write this differently, because I think there's a better way to write this. It seems a bit odd the way it's written. But yeah, that's cool. Are these in ints here though? Signed ints, because they're allowed to go into the negatives. Yeah, maybe we can. Yeah, so this would be the Morton code. Non-leafs be leaf nodes count. Right, so these are different sign. Okay, that's cool. D is diff. So with all right, so this is fine. I've read this and compared it, but what about the rest of it? So find the other end using the search. So it's doing a sort of like a right. So it's meant to do a for loop, but so okay. I don't get what this means. For every t, a half, a quarter, an eighth, and then it's going, and there's like a 1 in there. So yeah, I guess it's just saying keep dividing by until you get to 0. Sorry, dividing by 2, or keep shifting right. So it's doing this sort of like so it's in this L1, sorry, L max shift right. You got this thing called T here, so that's T, so it's L max. So it would have been 2, but you would have, yeah, made that right. So you're finding the other end of a binary search. Okay. So obviously the reason why it does the shifting left and shifting right is because obviously the nodes that are higher, they span massive areas. So you don't want to scan over every single node. You want to skip a whole bunch, I think. That's the basic idea. Is that right? iTemp. Yeah, there's a bit of skipping with this multiply, I think. So, yeah, and obviously this skip gets bigger. So do that there again. So, yeah, it's just looking at finding the other end of it, but doing a similar sort of method, but going the other way. So it goes to the left instead. So it will keep moving. This index is a bit fishy. So I remember so I think when we want to turn that into leaf node index, because it's not a one-to-one map anymore because we've got 4 nodes instead of 2 for every child. And then, right, so that helps you compute that range. So it's greater than node, then and then the result is basically doing a output child pointers. I'm right. See, you're not finding the other side though. Hmm. Yeah, so if... Yeah, you need to swap them the other way around. So it's... let's just store in a temp. Right, so range equal... Alright, so that'll do for now. So I think we need to... You know, we've got to find a way to draw these ranges. Yeah, so this just gives us the range of nodes. But it doesn't give us... You still need to do another binary search afterwards to get the... what is this doing? Right, but the blog post suggests another binary search after. Determine the split when you find... Yeah, and then you find the node. Split. But ours is going to be a bit different because it's not binary tree, isn't it? But I think we've got to test that we get the range working first. So how is it going to be a good way that we could test this range out? I think maybe... Yeah. We can maybe write it in number form, but I don't know. See, the range here is just drawn as this bar, the range of nodes. So the problem is I haven't built the tree yet, so it's hard to debug that. I could maybe try to implicitly build the tree based on the numbering scheme, just build it in this very weird... You know, if they're less than half, it goes back, you know, or... You know, 3, yeah. 3 is the parent of 1 and 2, but if not, then 4 is the parent of 4, 5 and 6, that sort of thing. Is there a particular reason why I want to do the GPU? Yes, because it'll be quick to do it. And then I can also construct it. Yes, I can construct it fast. I can construct it every frame. I can maybe construct multiple per frame. And yeah, that's it basically. So it's fast. Yeah, maybe I can build another... So just link up. Yeah, maybe you could say there's 4 children at 4. So it'd be like 1, 2, 3, 4, 5. Hmm. And they're all siblings. So 0 would be the root. Yeah, so I need some temporary code which will link up the parents to the children in a similar way to the way the algorithm's going to do it. So I can maybe debug visualize the range, or maybe we just start very small and just print them out. Yeah, maybe just print them out. Internal node, and then it has a range. I think this will just be better, and we can get it the debug visualization. So range.x, range.y. Y meaning end, x meaning start. And that one meaning internal node. So that would be, what exactly? I don't think I want to draw anything just yet. Right, so see what sort of ranges we get with these. So with one leaf node, your one internal node, its range is 0 to 3. That's perfect, right? But watch it fall apart. So 5 leaf nodes, which we can't see anything. Yeah, maybe I should have just enabled them. But yeah, 5 leaf nodes. Internal node 1. You know, let's get the old drawing up because it's going to be useful regardless. There we go. So, right. But with 5 leaf nodes, so 1, 2, 3, 4, 5. So this would be different, right? So it's saying the range of 0 is going from 0 to 4. So, what's 0 to 4 mean? Oh, of the leaf nodes. And then the range of 1 is going to 3 to 3. Yeah, I think that's a little bit wrong. Also, these ranges inclusive or exclusive. Got to think about that. So yeah, I multiplied it by 3. If I undo that multiply by 3, by the way, you'll see a very different thing. Here it is, multiplied by 3. Because I have less number of internal nodes than that binary tree does. So yeah, here you're going to see it like a binary tree, I think. Right, 0 to 3. Oh yeah, because that's the root node as a special case. The root node, if it's the root node, it will just do 0 to leaf take 1. So that's basically avoiding the whole complicated bit of code. So then 1 is going to be 1 to 2. Determine the range of leaf nodes that we are going over. So 1 to 2. Hmm. Yeah, something's not. Yeah, it's definitely not right there. But yeah, I think so. I think what we need to do next is go over these. We need to go over this function and figure out what it takes for us to. So I think we need to change this comment up a bit. I need to remove. This one works on each layer and checking one bit at a time. I think we need to check 2 bits at a time. Or we need to have a difference of, well, not check 2 bits at a time. We could just say what is the nearest. You could probably just AND it with the not of 1. So you're saying just remove the odd bit from the result of the count leading zeros. So if the count leading zeros is an odd number, it'll round it down to the nearest even number. So you're returning groups of 2s, which are the same, but they're not. But the 2s are next to each other. So hopefully that's all right. Because remember, 2 bits gets you 4 nodes. So that should help. So I think that's one of the things that we're missing. But it's just a guess. But there's also like a -1 and a +1 here. Which does feel a bit, I don't know, a bit fishy. Yeah, so the 0 node spans over 0 to 15. We can basically ignore this one. The 1 node spans from 3 to 3. That's weird. 2 spans from 6 to 5. No. It's kind of going the wrong way around. But there is that sort of switching thing here, diff. Right, switching that diff around the other way around seems to have changed it. Seems to have changed it the other way around, but you know, it's still off, I think. Yeah, the ranges are still a bit off. It's hard. Yeah, I need to think about how we could. Maybe we just start small and try and get those to work. Or maybe sort the numbering. Yeah, not sure yet. Right. Okay, I need to actually start packing up now. So I'm not on Tuesday or Thursday. I'll be going to work, so I'll go into the office, so I'll be kind of away for those days. But so the next stream is actually going to be on Sunday next week, and then we'll obviously get back to the regular schedule. So next week we'll resume with this. We'll try and figure out how we can debug, visualize it while trying to develop these complicated algorithms, basically, because it'll be a big help be able to visualize the data. Yeah, we made a good start at least on visualizing it. We just need to figure out how do we incorporate, how do we do it while we're building it. So yeah, let's find somebody to raid. Right, it's raid last miles. Okay, guys, thank you all for coming. I'll see you all next Sunday. Have a good week, and yeah, I'll see you all then. Catch you later. Bye bye.